Okay. So here is our boost converter. As you already know, this is just like a buck converter, except you rotate the components, the three components counterclockwise. Now you have the inductor at the input stage, switch in the middle, and a diode at the output. And just by looking at this, we can tell that a buck converter will have a good input current characteristics and bad output current characteristics. Why is that? Because we know that the inductor current is going to be a triangle waveform, right? And then the diode current waveform is going to be choppy, right? It's going to be a pulsating trapezoidal, right? Discontinuous waveform. So it's far away from DC. So when it comes to the quality of DC to DC converter, remember this is DC to DC, right? Input is supposed to be flat, output is supposed to be flat. So if you just look at the three power stage components, inductor, diode, and switch, look at the input current characteristics, we know it's going to be triangular waveform. That's going to be continuous. That means it's good. That means it's good. And then on the output side, you have a diode that would be turning on and off, on and off, on and off, which means the current is going to be also on and off, right? So it's going to be discontinuous. So bad output current characteristics, meaning you're going to have to put heavier filtering at the output compared to the input. Okay. Now, also notice that since this is important, this is practical aspect of boost in terms of application of boost. Notice that since inductor is at the input, therefore a boost converter is ideal for any current source, any source that acts like a current source, right? Such as solar panels. Solar panels outputting DC, but if you look at the model of a solar panel, it's usually modeled as a current source, right? So having inductor at the input would definitely be ideal for current source, right? Because current source means current needs to be constant, or close to being constant, right? So this will help definitely for current source type of applications, such as PVs. Okay. Yeah, we are not going to cover current source converter in this class. There are such things, right? What we are learning in this class is all voltage source converters, right? Meaning the source is always going to be voltage source, right? In EE410, which is not offered this year, only offered once every 2 years, I usually cover the other type, which is the current source converters. All right. Any question on this? So we derived the transfer function using volt-second balance. I always emphasize that you need to memorize, volt-second balance, VL on, T on, VL off, T off. That's the basis for you to be able to derive transfer function easily, rather than using other methods, right? This is pretty straightforward. VL on, VL off, T off. For most cases, T on is dt, T off is 1 minus d times t. Pretty soon you learn that in one of the converters, T off is no longer 1 minus d times t, but in most cases, this will work. This will definitely something that you can use, right? And then all that you need to do now is to just find VL on and VL off, right? To get the transfer function. So you go back to this basic topology of a boost converter, and you can find out what VL on is and what VL off is, simply by looking at this circuit, right? So what happens when VL on? What happens when we have when the switch is on? That's what I should say. What happens when the switch is on? That's VL on, right? And then what happens with the voltage across the inductor when the switch is off? So you can go through this, easily, hopefully, once you know the circuit. For example, VL on. We went over this last time, but I'll go over this again quickly. VL on means voltage across the inductor when the switch is on. When the switch is on, we learned that diode is off, right? If diode is off, then you can see that a voltage across the inductor right there must be V in, right? Because this is a short. By KVL, we can simply see that voltage across the inductor is V in. So right away, I know that VL on is V in. What about VL off? VL off happens when the switch is off, diode is on. So this is a short now. right? This is a short. That means this node right there is the same as that node. So that's V out, right? That's V out. So therefore, when the switch is off, voltage across the inductor must be V in minus V out. That's all you need to derive the transfer function. VL on, VL off. VL on is V in, VL off is V in minus V out. And you just plug it into this equation right there, and you get this transfer function right here, right? Right there. Okay. Now
I know you've said this like 6 times, but that it actually really clicked that time for some reason for me.
Oh, okay, good. Yeah, so as you are going through this exercise more and more, right? I'm pretty sure you're gonna do this much faster than what we've done in the past, right? Now you know what to do. Now it's gonna be very quick for you to derive this, okay? But I think the more important thing is make sure that you understand it, okay? Make sure that you understand why I do that, right? Why this is V in, why this is V in minus V out. All comes down to volt-second balance, okay? So not just understanding the algebra, of course, but understanding why this comes about. All right, so for a boost converter, that's what we have, right? And we learned that since duty cycle is from 0 to 1, so therefore output voltage is always higher than the input voltage. That makes it a boost converter, meaning a step up converter, right? Output voltage is always larger or higher than the input voltage. Nice, right? A buck converter is the opposite. So if I go back to, if I go back to this previous circuit right here, right? Right. What's interesting is that by moving the inductor from the output to the input, right, we are reversing the function of the circuit, right? In a buck converter, the switch is at the input, right, and then the inductor, right, the critical component, right, the heart of the converter, that's what I call it, the heart of the converter, is at the output for a buck. So that would give us a step down. Once you put that heart of the converter at the input, it becomes a boost, right? Guess what happens if I put that inductor in the middle? That's going to be a buck boost, right? So anyhow, that's later. So now we know that this is a boost converter, and a boost converter has inductor at the input, right?
So essentially you're just charging the inductor during the off time for this circuit and then using its stored energy to boost the output voltage?
I think you said it the opposite. You said charging the inductor when the switch is off, you said?
Oh, when it's on. Yeah, sorry.
When it's on, yes.
Yeah.
So you're charging when it's on. Yeah. Does that answer your question?
Yeah, I'm just kind of thinking out loud, I guess.
Okay, no, that's okay. So good. All right, so we also looked at last time the waveform, the shape of the waveform for the inductor current, right, using LDI, LDT. And we learned that the slope for charging the inductor is linear, just like a buck. And then when it's discharging, it's also a linear slope, just like a buck converter as well. And important to know is delta IL right there. This is one of the important equations that you need to know, right? Delta IL. What is delta IL again? That's just peak-to-peak inductor current ripple, right? So the previous one I showed you, sorry, let me go back. Yeah, that one is for on, right? This is the equation for delta IL when it's on, which should be the same amount of delta IL when the switch is off, right? Otherwise, it's not going to be a steady state condition. So delta IL off will have different equation, but if you plug in the values, you'll get the same magnitude of delta IL. And here's delta IL, I believe, right here coming up. Where is it? Right there, delta IL off, right? You can see the equation is different. It's longer equation, right, than the delta IL on. But if you plug in all the values in the equation, and then the same thing for the other one, plug in all the values for delta IL on, you should get the same delta IL, right, in terms of magnitude. They should be the same, right? So why is it important to know delta IL on? Because we use this equation for many things, right? As you saw as well in the buck converter. So between the two delta IL equations, I usually pick the simpler version of delta IL equation to plug into other equations that require delta IL, right? I believe for a buck converter, delta IL off equation is simpler than delta IL on. That's why in many of the equations in the buck converter, whenever we need delta IL, I usually plug in delta IL from delta IL off instead of delta IL on. But it looks like for a buck, for a boost, delta IL off is longer than delta IL on. Am I right? Yeah, see, delta IL on is just V in over L times dt, whereas delta IL off, you can see is longer. See that? Okay, it's just preference. I might do it differently in the book, but just keep in mind that either way is fine. Okay, if you want to use delta IL off from here or the other one, it's okay. Right? It's just whichever one you want to choose, right? So I hope that I choose the simpler one when deriving the other ones. When deriving other equation using delta IL. All right, okay, going back to here. Now that we know that our inductor current looks like a triangle wave, right, like that, just like a buck, of course, under CCM. Three things that we need to know, just like in a buck converter, okay? I'm gonna do it faster this time. 3 different values, okay? We derived this in a buck converter. I'm gonna derive it again for a boost, except, faster. The 3 values that we need is IL average, right? This is IL of t, by the way, right? Waveforms, right? IL of t, that's not 2, that's L. All right, we need IL average, the average value of this waveform, and then we need IL max, and we need IL min. Again, why? Well, these 3 values are needed for deriving other equations, okay? That's why it's important for us to know IL max, IL min, and ILT. And IL average, sorry, IL average. Now you might ask, okay, well, don't we know what IL max and IL min is because we know delta IL? Well, not necessarily. You do know delta IL. It doesn't mean you know IL max, IL min. How come? Well, because IL average changing, right? IL average is not a constant value. It is a constant, but its value depends on output current, right? As the output current, as the load demands more energy, this IL average goes up, right? And then when the output current is idling, for example, or is not requiring that much current, of course, IL average will be decreasing. Delta IL, however, is not a function of output current. It will stay the same. So delta IL stays the same, but imagine this average value, the dashed line right there, will shift up or down depending on the demand from the load. Does that make sense? Or any question on that one? So that's why just knowing delta IL does not necessarily mean that you would know IL max and IL min. Because what if I give you a different average output current, right? Then IL max is going to be different, right? IL min is going to be different. They're going to be shifted based on IL average. Agree? If IL average goes up, then of course IL max and IL min will go up proportionally, right? So so be careful, right? Now, of course, when it reaches boundary conduction mode, right, we will know what IL min is by knowing delta IL, right? If it is reaching, I'm just going to draw it. If it's reaching boundary conduction mode, this is a special case, as you already know, right? At boundary conduction mode, we know right away that IL min is 0, right? That's 0 amps. If you know delta IL, of course, you will know right away IL max, because IL max is going to be equal to delta IL, right? At boundary conduction mode. Okay, and then we know average value as well, which is going to be delta IL divided by 2. Any of the things that I just mentioned does not make sense to you? You need to let me know now. Okay, if all of them make sense to you, then let's move on. Okay, now let me go to this other page. Again, our objective now is to determine IL, IL average, right? IL average. Right there, IL max, IL min. Okay, now in a buck converter, I'm going to draw a buck converter. This is a buck converter right here, right? We also did the same thing, right? We found IL average, which is right here. Okay. Now IL average in a buck converter is easy, right? We know that by KCL, IL is equal to IC plus I out, right? But when it comes to average value, we know that IL average must equal to I out average because IC average is equal to 0 by M second balance, right? So for a buck converter, it's straightforward. IL is just equal to I out. Now, why is it important for me to relate IL to I out? Anybody? Why is it important for me to relate IL to I out? And anybody knows the answer?
Is it so that you can like determine the sizing of L for like a certain load?
Yes. So the reason why we have this, very good. So because whenever we are designing a converter, right, eventually we're going to be sizing components, including knowing IL average, right? That would be required. For example, in sizing switch current rating, diode current rating, you're going to need IL average. Now, when you are sizing, I mean, think about it from the practical point of view, right? When you're designing a converter, don't you want to design, don't you want to size the components or understand current or voltage, average value, RMS values in the circuit based on what's given or based on the given parameters for the converters or based on design specifications that are provided by a customer, for example, right? So that's very important. It's very important to be able to do that, to be able to, like I said, size components or look at different quantities in the converter based on the value they are given, right, before you even design the converters. And I already mentioned this maybe at least 3 times that when you're designing a DC to DC converter, what are typically given? Okay, can you answer that before you design? Come on.
Input voltage.
I'm going to wait. What would be typically given before designing a converter? Before you design a converter, you need to know some parameters, right? Some design specifications. What are those?
Output power.
Output power, very good. And specifically max, okay? You need to know max output power. What else?
Input and output voltages.
Input and output what?
Voltages.
Very good. V in and V out. And V in is typically given in range, right? V in min, V in max. V in max, okay? So at least you need 3 of these values. You need these 3 values, at least. P out max, V in, V out. And then again, in most cases, V in will be given in terms of V in min and V in max, right? So that's why very important for us to be able to relate all the design equations within the converter using these 3 values, right? Because those are given, right? Those values are typically given. So why not use them, right? So that's why, going back to my original question, why is it that it is important for us to relate IL to I out? Well, because I out average typically is given, right? How? Well, from here, V out max and V out, right? We can see that I out average is equal to P out divided by V out. Make sense? So for a buck converter, that's just equal to P out over V out. Of course, for worst case scenario, you want P out max, right? That's going to be the maximum value of the average current through the inductor. P out max over V out. But in general, IL average in buck converter is equal to I out average, which is equal to P out over V out. Any questions on that? So again, I like you to understand the concept, not just the equation, but why things works like they're given in the book, right? It's not just plug in chug, but understanding what goes behind every equation.
I had a question.
Sure, go ahead.
We're ignoring IC because ESR is so insignificant. Is that correct?
It's not. We're not ignoring IC. We're looking at the average value, right? So IL average is equal to IC average plus I out average, right? What is the average value through the capacitor? Average current value through the capacitor?
0.
0, yes. Amp second balance, right? That's one of the
I see.
midterm questions, I believe, right?
So
What is-
sorry. Yeah, I
No,
thought,
it's all
I
good.
thought
It's
there
all
was
good.
AC. You're right.
It's all good. Yeah, make sure that you ask, okay? Make sure that everybody understands that. Good? All right. Now, that's a buck. A boost is different. Boost looks like this. Oops, right there. Okay, so that's our boost converter. Right, again, we're interested in finding IL average. That's our IL. Now it moves to the input. So I know that for sure that IL average is no longer equal to I out, obviously, right? Because input, so because inductor is at the input now, right? So this is no longer true. What is true is that IL average is equal to I in average, yes? So then now the question is, how do you relate, right? If you look at what's given, V out max, V in, and V out, I don't see any I in there, right? I don't see any P in there. If I know what P in is, then I in would be just P in over V in, right? So again, it would be nice if I could somehow relate this to I out, because I out is given, right, in the design specs, right? So understand the problem here? Well, if that's the case, then I don't think that's a problem at all, right? If we know what we're doing, right? Remember that our analysis is ideal, under ideal condition. And as we know, under ideal condition, P in is equal to P out, right? All of the stuff that I'm writing right now is in the book, okay? So you don't need to write or take notes. So you can see that P in is equal to P out under ideal condition. That's what we're doing. That's what we are doing now, right? Ideal analysis, right? Ideal analysis under ideal condition. There you go. So therefore, we know that P in is equal to P out. If that is the case, then I know that V in times I in is equal to P out, right? And watch, look what happens here. I in is equal to P out over V in. Isn't that good news for us? Because now I know how to relate IL with what? With parameters that are given in the design specifications, right? Namely P out and V in. You see that? Cool, huh? So then, so that's how you would find IL average for a boost converter. It's not as straightforward as a buck, but it's not bad, right? If you know what you're doing, like I said, right? If you know that this is an ideal condition, then you would know that P in is equal to P out. And so simply I in must be equal to P out over V in. You agree with that? All right, so then when it comes to worst case, what is IL max then? If you need to find this, which you do for sizing switch current and diode current, how do you find IL max, meaning the worst case scenario for the average value of current through the inductor? How would this equation change? Anybody? Come on, I'm giving you a turn to speak.
Max.
Say it again, sorry, louder.
We just use P out max.
Just P out max. So what if input voltage has a range?
V in min.
P out max over
VN min.
over what?
VN min.
V in main, yes. P out max over V in main. Okay, right there. Right. Trust me, I use this equation a lot. Every time, I should say, not a lot, but every time I design a DC to DC converter, I use that equation. I need IL max to size my to size the switch and the diode. Right. Okay. So P out max over V in main, or in general, this is the equation. That's in general, P in over V in. But if you want to do the worst case, P out max over V in main. Okay, so that's how you get IL average. Back to here, that's what I have right here, see that? And then I can always expand the equation, right? That's what I did right here. I expand the equation. You can see yourself what I did here, but anyhow, once you understand the process, going from going from IL to here, right? Or basically using this equation. If you understand that, then if you understand going from here to here, then the rest right here, the whole thing right here is just a different way, different ways of expressing IL average, right? For example, I replace P out with V out squared over R, right? And then you have the ratio of V out over V in. By doing that, and we know that V out over V in for boost converter is 1 over 1 minus D times V in, and so on and so forth, right? And so now I have another equation for IL average. Okay, so there are many forms of the equation for IL average, but the basic equation or the initial equation is right there. Okay, any question on this?
So wait, Tawfiq, if we originally said P out over V in order to get IL max, we wanted a minimum V in.
Yeah.
In the second version, the final version of the equation where you have V in over 1 minus D squared RO, would that still hold true, or would you want to say have RO min and V in max?
Yes, exactly. Just the last part of the statement you have, that's the correct one, right? This is all general equation, right? There's no V in min, there's no V in max. This is just one V in. And if that's the case, then if you want to get the worst case for the last equation right there, for this last equation, then yeah, you're right. This is going to be V in max, right? And this is going to be R out min. So depending on which equation you use, that's going to determine which of the input voltage range you need to use for the equation. Okay, if you use the first equation right there, it's getting crowded, huh? Yeah, if you are using the first equation right there, obviously you need to use V in min. But if you use this equation right here, you need to use V in max and R out min. Does that answer your question?
Sort of. I guess I'm not really seeing what the difference is between those two, because if they're supposed to be equivalent, is there like an assumption being made for the second equation that the first one isn't?
Okay, think about you have different equations, but they give you the same answer, just like delta IL. Remember delta IL equations for delta IL on, delta IL off? They're totally different equations, right? But then you get the same answer. Same thing here, right? If you look at the equation for delta IL, how come they're different for delta IL on and delta IL off, right? So they're both from the same condition. Same thing here. By rewriting the equation different way, you have to apply different different parameter in the circuit, in the equation, sorry, right? Mathematically, I mean, you can see, mathematically, that's what you need to do, right? This is going to be V in max, that's going to be V R out min. Because why? Well, because we just changed the equations, right, to get the same thing. Right? And don't forget that this D is also, if this has to be a max, that D has to be D min, right? And what is D min? So D min is equal to what? Well, you have to find the equation for the D for the boost, right? V out is equal to 1 over 1 minus D times V in. So man, so you solve for D basically, right there. Oh, it's not bad, right? V in over V out, and then D is equal to 1 minus V in minus V out. There you go.
Okay, that's probably where it comes in, or in the equivalence.
I think so. Yeah, it's all embedded in this equation because again, you expressing the same parameter IL average with respect to different values in the different quantities in the circuit. So things will change accordingly, right? So, but again, like I said, you know, the answer should give you the same result.
All right, thank you.
Okay, you're welcome.
Professor?
Yeah.
Just quick thing, it looks like you have a typo in the derivation for the first IL average.
Oh no.
You added in a P out V in. I don't think that the V in.
Oh,
Yeah, I noticed that too.
what is it? What is it? Oh, this should be crossed out, huh? Is that what? Yeah, it is.
Yeah.
Sorry, could you please fix that? Thank you for catching that. Thank you for catching that. So please cross that out. There's no V in for that equation, for this equation right here. Thank you. Okay, any other comments? Again, please cross this out one more time. Okay. All right, no question, let's move on. So from there, I get IL average, and then finding IL max, right, will be following this equation. It's going to be IL average plus delta IL over 2, exactly the same as what we did for boost, for buck converter. And now you just need to plug in the equation for IL average right here, right, from the last equation, you just plug in. And then delta IL, you have the delta IL equation previously, remember? And oh, just like I expected, I use the delta IL on equation. See that? That's from delta IL on. How do I know that? It's V in times dt. See that dt right there? That's T on. Right? And I'm not using delta IL off because remember I said earlier, delta IL off is a longer equation. So why use a longer equation if you can use the shorter one, right? So same thing here, IL average minus delta IL over 2 for IL min, right? So that should be good, right? Any question on IL max and IL min? Now you have the equation for IL average, IL max, IL min. Why do we need IL max? Anybody from the discussion in the buck section? Where is IL max useful in terms of sizing components?
Want to get the rating of the inductor value to see if it can handle the current?
Very good. IL max determines saturation current rating of your inductor, right? Or IL sat, right? So that's something that you need to know. Make sure that IL sat of the inductor that you're buying will be larger than IL max at full load, of course, right? Remember that IL is always changing depending on I out. So make sure that IL sat is larger than IL max at full load condition. All right. IL min, where is this useful? Well, if you are sticking with the textbook method for finding critical inductance, then IL min will be useful because I can just set IL min to be equal to 0 for boundary conduction mode. Remember boundary conduction mode, IL min is equal to 0. You set it to equal to 0. And then you can see that I'm using the same exact equation right there, right? Put it here, and you can see that there's an L in that equation. That's what we're aiming for, right? Solving for L. So under boundary conduction mode, you can solve for L because IL min is equal to 0. Then solve for L right there. And at the end, you get L critical inductance equal to this equation, right? So that's one way to determine critical inductance. Notice that again, typically F will be something that you are either given or you have to choose, right, to be able to size this properly. However, what's more important is I out min. You see that right there? I out min average. that corresponds to how low of average value of current on the output, right? How low of the average output current, I should say, before the converter reaches this continuous conduction mode, right? So this I out min refers to the time or the value when IL, this is IL, is reaching boundary conduction mode, right? Remember, this is I out, this is IL, two different things, right? So as I out is being decreased, right, inductor current will also decrease, right, accordingly. And if you keep decreasing I out, then eventually IL is going to reach BCM, right? IL min is going to be equal to 0. When that happens, that's what I out min is. That's what I out min that you put in. So in this case, of course, I out min will be delta IL divided by 2, right there. That's your I out, that's IL min. So sorry, I said it wrong. I out min, I out average min happens when we have IL min average, right there, right? So now you have to relate IL min to I out min. Okay.
Wait, sorry, can you say that last line again? How do we get I out min from IL min?
We got it from the equation of, P in is equal to P out, right? So P in is equal to V in, I in, yeah, just like the previous derivation I did, which is equal to V out, I out, right? You can see the relationship there.
Yeah.
Right? We know that I in average for a boost is equal to IL average. So that equation is actually equal to V in IL average times V equals to V out times I out average. See that? Does that answer your question?
Yeah. Okay, so you're saying to use the IL min in that formula to get our I out min.
That's correct.
Got it.
Yeah. Right. So I don't know if you noticed that every time I'm trying to find a parameter, I always try to express them in terms of, as I said earlier, in terms of the given specifications, right? Namely, V out, V in, and P out, right? So keep that in mind. So otherwise, it'll be hard for you to calculate those, right? Okay. Now that's critical inductance using textbook method. Practical method, lots of friends in Silicon Valley, they use this method. They will say, okay, just instead of using that equation under BCM, just pick a value of delta IL between 30% to 40%, right? So just pick. Now, yeah, this is kind of random, of course, but this is based on experience, of course, practical experience in terms of the balance between the size of inductance and then cost and then stability as well. That's an aspect that we're not going to cover in this class. So that's in 527. So based on those different effects of sizing of how big the inductor is, based on their experience, they found out that between 30% to 40% would be a good starting point for delta IL, right? So what does that mean? 30% to 40%. That means that delta IL just pick between 0.3 to 0.4 of IL average. Okay. Of course, you want this to be what do you call it? Worst condition, right? So that's going to be off IL max, right? And how do you find IL max? Well, that depends on the converter. For a buck, we already know that's going to be P out over. Oh, sorry, for a buck, that's easy. Let me erase this. For a buck, that's going to be the same as I out max. For a boost, that's going to be what? P out over P out max over, we learned it earlier. V out.
V in min.
Yeah, V in, oh my God, yeah, you got it. I put V out min, it should be V in min. Very good. You've been paying attention, very good. All right. That's it, right? For buck, boost, and then for buck boost, I think you will know right away after you see the circuit, of course, what needs to be done there. A buck boost is going to be a bit more trickier than a buck and a boost, of course. All right. Any question on this? So pick delta IL between 0.3 to 0.4 of IL max average, IL average max, I should say. Okay. Now, once you determine delta IL, then use VL is equal to L DIL dt. Very simple method. See that? All you need to do is go back to this basic equation that VL is equal to L DIL dt. If you use delta IL on for a boost, that's going to be equal to V in, right? Remember earlier when the switch is on, voltage across the inductor is V in. So V in is equal to L delta IL delta T, and you have delta IL right there, and the only unknown is L. So from there you get your equation right there. See that? V in, duty cycle, and then delta IL that you pick between 30% to 40%, and then frequency. Very simple way. Any questions?
So Professor, in the homework problems and practically speaking, we will always be picking delta IL?
Oh, no, not really. You have to look at what's given in the problem.
Okay, so if something's missing then from like a formula to determine delta IL, then we'll just make that value up between the 30 and 40%?
Yes, sir. But, but yeah, I think in the homework problems, most of the homework problems, if I'm not mistaken, I use the textbook approach, right? So that you understand how to go through that, exercise of using the textbook method, right? But keep in mind that that we also have this option of using the practical method. Okay. In the future, if you are working in this area, TI, Maxim, ADI, MPS, I know I'm forgetting some other companies, go ahead and use this method, right? It's a much easier method than the textbook method. Okay. But yeah, if you see a problem in the finals, I already if I state in the problem statement that delta IL needs to be 35%, then you know what to do, right? That's 35% for delta IL with respect to IL max. Or I might say alternatively, using the textbook method, I might say the converter will maintain CCM down to 20%, for example. That's going to be textbook method, right? Because it's using BCM method for that kind of statement.
Professor?
Say it again?
I had a quick question about IO max previously. So when you say we're running for buck converters at full load, does that mean minimum resistance and maximum current?
Yes.
Okay.
If you translate current into resistance by Ohm's law, yes, then that R is going to be R min. Yes.
Wait, so a full load is R min?
Of course.
Right.
Because I out is equal to V out over R, right? If you translate current into resistance, then R is equal to, then I out max must be equal to V out over, which one, R min or R max?
R min.
R min, yes.
And then, okay.
Sorry, I didn't mean to cut you off.
I'll just be quick. Our delta ILs are then based off of our Ls. You'll give us our L, and then we find delta IL off of that for both buck and boost converters.
Oh, sorry, say it again, say it again.
The delta IL, we typically find that given the inductance value, right? For buck and boost converters?
No, okay. From practical point of view, typically we pick L first.
Yeah.
We pick L by assuming some delta IL.
Yeah.
Okay, is that what you meant?
No, I meant in the textbook problems. Sometimes you give us L. Do we use L to then find delta IL for buck and boost?
Yes. If I already give you L, then that's easier, an easier problem, right? Because then you don't have to worry about delta IL. You can calculate delta IL based on L, yes.
Okay, thank you.
Yeah, so you can use this equation too, actually, right? You can use this equation. If you already know L, then yeah, just use this equation, except now you're looking for delta IL instead of L, right? Okay, does that answer your questions?
Yeah, thank you.
Okay, good. Now I can also use off time instead of on time, right? You can see that if I use off time, it's a longer equation, but I'm going to put it right here just so that you know that we can use either one of the equations, and it should give you the same value for LC, right? Okay. Moving on, IL max is equal to IL peak, right? For worst case scenario, you want IL max, the average value at maximum condition, which is at full load, plus delta IL over 2, and you get R out min. Some of you already mentioned in the questions, right? So it has to be R out min for IL max, okay? Because again, IL max relates to I out max. And I out max occurs when R out is equal to min R out, minimum resistance. And as I said earlier, IL set is being used to size the peak current of your inductor right there. So make sure that whatever you calculate, whatever you get from this equation right there, right? You put it into here and make sure that that value that you calculated is less than the IL set that you pick for the inductor that you will be purchasing. Okay.
Professor?
Go ahead.
When it comes to R out min, if the problem in the textbook gives us a resistor value, how do we know if it's the maximum or the minimum?
Yeah, if the problem only gives you one resistor value, then there is no R out min, R out max. This is going to be one R out.
Okay.
Yeah, so just use that R out for the equations.
Got it. Thank you.
You're welcome. All right, going back to this average switch current, I told you earlier that we need IL average to size current rating of the switch, right? As well as the diode. You can see how they're being used. Have you seen this equation before? Have you seen these equations before from buck converter? Yes or no?
Yes.
Yes.
Yes, exactly. You can see that the equations have not changed, right? It's the same. It's IL average times D for switch average current and IL average times 1 minus D for diode current. What makes the difference between buck and boost is what? The general equation stays the same. What changes for what is going to be the difference between the equation for buck and for boost from this equation?
The inductor current versus the source current?
The inductor current. Yeah, so you have the same general equations for a buck, for a boost, and for a buck boost as well, right? You can use the same equations, okay? This is the starting point to find I switch average current and I diode average current. These are the starting point. What makes the difference between all three, buck boost and buck boost, is the IL average value, right? We talked about it twice already, right? IL average for a buck is I out average. For a boost is going to be P out over D in. Remember that, right? So start from the same equation, but then make sure you change IL average based on the topology. Okay, so here is what I did right there. I derived the IL average based on the equation that we derived before, right? Right there, you can see that IL average is the same as IN average, as you already know, and so on and so forth. And at the end, I have a very simple equation right there, which I like right there, right? You can see different equations though, right? There are many equations to express I switch average. 1, 2, 3, 4, 5, and at the end I simplify into a much shorter equation. That's equal to di out max over 1 minus d. Right? Again, I like this equation because these are given in terms of these are expressed. I switch average is expressed in terms of given specifications, right? I know what I out max is because we know P out and V out. And I know D because I usually know V out and V in, right? As you know that D is a function of V out and V in, right? So that's a good design equation right here, right? Very practical equation right there. Any questions? Same thing with I diode. Right? I'm not going to go through this in details, but you can see, look, all of these, right? We know the general equation is IL average times 1 minus D. But when I derive those, look at the end. Does that make sense to you that ID average is equal to I out average? Does that make sense to you or no? That ID average current, the average current through the diode is equal to the average current through the output.
Yes.
Yeah, that makes sense.
Yes, right? Why? Because it's the topology, right? The boost topology looks like this. You see that? On the output side, we have diode. See that? I diode right there, and this is I out, and here's IC again, right? ID average is ID is equal to IC plus I out, right? If you take average value, then you can see that ID average is equal to IC average plus I out average. We know already that IC average is equal to 0, right? By amp second balance. So therefore, ID average is equal to I out average, right? So
Hey,
this,
Tawfik,
yes,
how would you get the peak diode current?
peak diode current. Okay, maybe wait. Okay, let's wait.
Okay, thank you.
Or maybe now. It's okay. Let me see. I think we're close. Or not. Oh no, it's not here. All right, I'm just gonna draw. I'm just gonna draw.
Yeah, I was working on the homework and I couldn't find it.
Okay.
Okay.
So here is our inductor current, right? I switch with respect to time, I diode with respect to time, IL with respect to time. What do we know about inductor current with respect to switch current and diode current? This also applies to buck and buck boost. We can tell by KCL that IL is equal to I switch plus I diode, right? Who asked the question earlier? Somebody?
I asked.
Oh, Emil? Is that Emil?
Yeah, that's me. Yeah.
Okay. Sounds like you. Okay. All right. So you just have to understand that I switch current and diode current all comes from inductor current, right? And we know that the switch current is going to be the portion of the inductor current when the switch is on, right? And we know that the switch is on, it's right there. How do I know that? Because the inductor is charging. How do I know the inductor is charging? Because that's the reason why I went over the ILDT, right? It's sloping up, right? It's ramping up, just like that, right? So therefore, I know that since inductor current, the charging slope comes from the switch, or goes into the switch, I should say. Therefore, the switch current looks like this, right?
Yeah, that makes sense because the current's not going through the diode at that point.
Right. And then when the diode is on, switch is off, then the rest of the inductor current flows through the diode. Can you actually?
Oh, so the diode peak is the same as the inductor peak then?
Exactly. Very good. That's why I'm drawing this, so it will be clear to you that IL max, another important thing about IL max is that IL max is going to be the same as I switch max, and it's going to be also be the same as I diode max.
Wait, is that average? I thought there was a difference between IL peak and IL max.
IL peak and IL max, they're the same.
Oh, they're the same? Okay.
Yeah, the peak value, right? Max is peak value.
I thought in the book that there was an average sign over all the IL maxes, but maybe that was me reading it wrong.
You mean like this? Yes? Like that?
Yes. Wouldn't that not mean that that's the true peak? Wouldn't that mean that's just the max average current?
No, so this means that you take the average value first and then find the maximum of the average value.
Oh, okay.
So that would correspond to this, Emil, right there. That's this. Right? If this is, if I draw this inductor current at I out max, then this is IL average max.
Wait, I'm sorry. I'm still confused. Why?
Oh, wait.
What's the difference between IL average and IL max average then?
Okay. IL average. Look, watch. Let me draw.
Wait, on the left there, yeah. Shouldn't it be Wouldn't that just be IL average, not IL max average?
It's going crazy here. Hang on. Okay. On the left, which left? Come on, it's doing it by itself. I'm not sure why.
Wait, I think I might understand. Are you saying that the instantaneous maximum is found by taking IL average max and then taking the peak of that?
Hang on. I'm not sure what's going on. Sorry, guys.
But how do you have a peak of an average?
Hang on. Please, hang on. I'm trying to do this. Okay. So first of all, you said somebody said about IL max on the left. What about this? Let's do it one by one.
So I'm saying that looks like when it's like max load or max output, basically when the power is maxed, then
Yes.
that's the average current at that max load.
That's what I put right here.
Yeah, but then IL max, I'm thinking, is actually the peak. I'm talking about the IL peak.
Yeah, so this is IL peak right there.
Yes, which is different than IL max.
Yeah, so unfortunately, when we're saying it, they sound the same. IL peak right here is equal to IL max right there. See that? I'm not putting the bar on top of IL.
I think in the book it has the bar though.
You know, I'm saying if I put the bar right there, that means
Yeah.
that's the max of the average value. But
Okay,
if there is no bar, then these two are the same.
got it. Thank you.
Okay? So watch out for that bar. If there's a
Wait,
bar,
can you clarify what the bar means? Like, how do you have an average of a peak?
so bar always means average, right? This is from chapter 2, right? Anytime you have a waveform with a bar, that means it's average. Anytime you have a waveform with a tilde, that's RMS.
Yeah.
Waveform with, hang on, every time you have a waveform with these symbols, that means what? Total RMS, right? So what is the question before I answer your question?
I was just curious what IL max average is compared to IL average.
IL average, it's not necessarily IL max, right? So that's why I was gonna draw earlier right here. See, it goes crazy again. I'm not sure what's going on. Sorry, guys. I'm just gonna draw it right here. Okay, do you agree with me that IL changes with I out like this? Whoever asked the question, who asked that question?
I'm asking the question, Josh.
Josh, okay, Josh, look, right? This is my IL of T, which goes up with I out. Yes?
Yeah.
Okay, if you agree with that, then watch. IL average, every single triangular waveform has IL average, yes? So here's IL average, here's IL average, here's IL average, right? You agree with that?
Yeah.
Okay, so I'm gonna call it IL2, IL3, and this is gonna be at I out max. When I put output power at max, right? That corresponds to I out max, yes? So therefore, the IL average that occurs at I out max must be IL average max.
Got it. Thank you.
I know it's confusing, but you know, it is confusing because we have different what do you call it, subscript, right? Along with the bars and the tilde. So make sure you ask the question.
Thank you. That actually helped me a lot too.
Okay, good.
I had a quick question on that.
Go ahead.
So going back to finding I diode peak, do you then find the waveform, with the average of IL max, and then take IL bar max and add I delta L or delta IL?
Okay, let me find that waveform right here. Yeah, so what I'm saying is that if you know IL, if you know IL, right? If you know IL max or IL and IL min, if you know IL max and IL min, then you would know ID max and ID min over here. values, points, I should say. That's not ID min. ID min is 0, of course, but I'm talking about these points right there, right? Because they're exactly the same as that point right there. See that right there?
Yeah.
Same thing with switch, right? If you know IL max, then you know I switch max, because they are exactly the same point. Same thing with I switch min on that point right there, right? So all you need to do is to find IL max, and then once you know IL max, that's going to be equal to I switch max and ID max.
And that would just be delta IL over 2 plus bar IL max, right?
That's correct. Yes, okay. That's correct. Very good.
Professor, sorry to backtrack. Would you mind going to that other graphic real quick? I just had one more clarifying question.
No worries. This one? Which one? This one?
Yeah, that one. So earlier you said that V in times IL min average equals V out average times I out max average.
Okay.
But doesn't that mean that IL min average is proportional to I out max average? So how does that align with what you wrote over here?
Can you state the first part of your statement?
My question is, in the equation V in times IL min average, you said that's equal to V out average times I out max average. So wouldn't that mean that at I out max, you reach IL min?
Hang on. First of all, this equation should be, in general, should be this. Yes?
Yeah.
Okay. And then what is the question now?
So what you wrote in this graphic was that I out max is related to IL max. But I thought you told us that IL min is in that equation you wrote at the bottom there.
IL min is equal to P out max over V in min. Oh, no. IL min, IL average, right? This is average value. I don't think I have equation for IL min. I have the equation for IL without the bar. I have this equation, but I don't think I have this equation.
Oh, did I just write it wrong? Is it IL max average?
I don't know.
I may have wrote it wrong.
I'm not sure.
I'm gonna assume I did.
Okay, but watch. Look at this equation right here, right? That's your first statement. Do you agree with me that from that equation, right? If I solve for IL, right there, that's going to be equal to V out, I out over V in. Yes.
Yeah.
So therefore, IL max must be proportional to I out max. Yes.
Okay, that was what I was clarifying.
Okay.
Thank you.
You're welcome. Voltage rating. So now I'm done with this current rating of the switch and the diode. Now, how about voltage rating of the diode and the switch? That should be easy, right? The voltage rating occurs when the switch is open. Same thing with the diode. The diode voltage is going to be calculated when the diode is open, right? So for a boost, when the switch is open, we know that that's not boost. For a boost converter, right there, when the switch is open, that means the diode is on, right? Like that. This is V out, this is V in. And look at, this is the switch right here that's open. What do you think the voltage across the switch is from here? You can see that's equal to V out, right there. Okay, oh, that's diode. Here's the switch right there. So you can see that maximum switch voltage must equal to the peak of the output voltage. Same thing with the diode. The diode has a maximum voltage when the diode is off. That means the switch is on, right? So when the switch is on, the diode is off. Here's the diode right there, and here's the output voltage right there. So you can see from this KVL that voltage across the diode must be V out as well. Okay. Any question on that one? Not. Let's move on. Okay, this is the capacitor. I won't go through this in details. Okay, if you missed the class on Tuesday, then you need to go watch the video that I posted on YouTube. I spent lots of time deriving the capacitors, right? There are 3 different ratings as you, what is it doing here? Okay, there are 3 different ratings for capacitors, right? Number 1 is the critical capacitance. Number 2 is the voltage rating. And number 3 is the RMS current rating of the capacitor. So I went through all 3 on Tuesday, and I provided 2 different examples, output capacitor and input capacitor of a buck, right? So the same thing here for a boost, right? In order to get the capacitance, you need to know the current waveform of the output capacitor and input capacitor. I don't know what this PDF is doing, is scrolling by itself. Oh my goodness. What is going on today?
Professor, do you maybe have like the space button stuck down?
Maybe, or just a ghost next to me. I'm not sure what happens. Okay. Anyhow, where was I? See, that's a buck. Sorry, guys. Where is it? Oh no. All right. So again, you need to know the shape of the current waveform through the cap in order to see. It does that again. In order to determine the critical capacitance. Okay. So for a buck converter, I'm just gonna do it quickly here. I wish I could find a point where I stopped early and it keeps scrolling by itself. I'm not sure why. I tried to use my finger and this is wasting time right now. I don't like this. Okay, right here. Okay. All right. I'm not gonna touch anything now. Well, I should touch my stylus right here. Okay. So when we have a boost converter right there, right? So just quickly, you can see that if you put the output capacitor, okay, can somebody tell me real quick that the capacitor current waveform must be derived from whose current waveform? I'm looking at the output. Whose current waveform? Diode, yes. That's why when I draw the current through the capacitor current through the capacitor current waveform through the capacitor, it looks like this. That's a diode current, isn't it? How do I know that's a diode current? The downslope, right? Right there. Okay. And then again, from there, you get the offset, right? Just like I did for a buck. And then you apply Q is equal to C delta V. And then from there, you get output capacitance. What about the input capacitor? Where is it derived from? Anybody?
The inductor current?
The inductor current. So therefore, when you draw the shape of the current through the input capacitor, it should be looking like inductor current waveform, which is a triangular waveform, right? So I hope this is not scrolling by itself anymore. Input capacitor, look at that. See that? That's input capacitor current waveform derived from inductor current. And then from there, you get the same thing. You apply the same thing. Q is equal to C delta V. And from there, you get input capacitance, critical capacitance right there, right? And then the RMS current rating, of course, is going to be depending on the shape of the current, right? If for a boost converter, if you are trying to calculate the RMS current through the cap right there, then you need to do the RMS equation, because that's not an easy shape to deal with. So that's why the equation is long. See that tilde right there? It means just the RMS equation, RMS value, AC component of the current, right? Not total RMS. This is just AC RMS. And you can see that we have a long equation right there at the end that you can actually apply, put into your design equation sheet to find the RMS value through the cap. For the input, is easy because that's triangular waveform. As you know, the RMS of a triangular waveform is peak divided by √3, right? So that's much easier to find. Right there, you can see peak divided by √3, right? Okay. All right. Any questions? Unfortunately, I'm not able to finish buck boost today, but it's fine. I'm happy that we clarify several things today from your questions. Look, this is the input-output current characteristics, right? A buck is bad, good. Boost is good, bad, and that makes sense, right? Because a boost is totally the opposite of a buck, right? Now, what's interesting is that when you do buck boost, right, which is next right here, and then I can adjourn after this. Let's take a look at the buck boost right there.
Hey, Tawfik.
Yes, go ahead.
I think buck boost is on the homework. Are you gonna leave it?
Yeah, no, it's okay. You can still do it. I mean, you have enough background to do the homework problems, right? It's gonna be the same. I can actually finish buck boost in 10 minutes, you know. But I think you have enough what do you call it, analytical knowledge right now to go through buck boost yourself, right? And understand where the equation comes from. But I was going to say that a buck boost is a combination of a buck and a boost, right? That's why it's called buck boost. Now, do you think that's such a good idea? Remember, buck is bad, good. Boost is good, bad, right? So now a buck boost is a combination of buck and boost. Buck is bad, buck at the input, boost at the output. At the input, this is buck, and this is boost. At the input, buck is bad. At the output, boost is bad. You see that in terms of input-output current characteristics, and this is one way to combine them. Of course, we have other ways to combine buck and boost. But anyhow, you can see that input stage looks like a buck. How do I know that? Because at the input we have a switch, right? And look at the output. As a diode, just like a boost, right? So therefore, now we know that that this topology is a combination of a buck and a boost. That's why it's called buck boost. And okay, in 1 minute, right? I'm going to challenge you right now. In 1 minute, how do you derive the transfer function of this? Pretend this is an interview question. How do you?
Volt second and amp second balance.
Just volt second balance, okay? Volt second balance. Okay, can you apply volt second balance? Somebody, what's the first equation you should write?
VL on T on plus VL off T off.
Okay, I'm gonna write it. I'm gonna write this and see if we can finish in less than 1 minute. VL on T on plus VL off T off equals 0. What else? And then what? What can you know from this equation? Which part of the equation you know?
You can use duty cycles, right?
Exactly.
VL on times D plus VL off times 1 minus D equals 0.
Don't forget the T. Okay, right there. Okay.
Oh, yeah.
And then now it's just a matter of looking at the circuit and determine VL on and VL off. Can you tell me what VL on is quickly?
VN.
Exactly. VL on happens when the switch is on, the diode is off. So you can see clearly that when the switch is on, voltage across the inductor is straight into VN. Okay. Well, how about VL off?
VO.
Ah, sorry. Okay. See, VL off means the switch is off, the diode is on. See that? When the diode is on, the switch is off. We can see right away that VL on is straight looking into the output, right? So that's going to be V off, V out. See that? You're almost done. So what is V in over? What is V out over V in from here? That's an easy algebra.
Negative D over 1 minus D.
Exactly. You see that? You finish in less than 1 minute, or maybe 1 minute. You see how easy it is to derive transfer function for a buck boost and buck boost if you stick with volt second balance, right? Look at the transfer function and then we can adjourn. Look, what can you say about the transfer functions? D and then times 1 minus D, right? What about this D? Where is that coming from? What transfer function is coming from?
Buck.
Buck. Where is that 1 over 1 minus D comes from?
Boost.
Boost. That's why it's a buck boost function. So from this topology, you get buck and boost. You can step down and you can step up. The only problem is it has this negative sign in front, right? For some application, that could be a problem. Anyhow, we are done for today. And you can see my point is that after going through the exercise of deriving transfer function twice, you can see how easy it is to derive the transfer function for a buck boost. And not just for a buck boost, I'm telling you, it's also for other topologies, right? It's just going to be simply applying volt-second balance. VL on, T on plus VL off, T off equals 0.